Okay, we've all been there, right? You're staring at that 9 by 9 grid, just trying to figure out where that last 7 goes. Sudoku, it seems like a pretty simple, harmless logic puzzle. But what if I told you that every single time you play, you're actually tapping into one of the most mysterious processes in all of physics? I mean, the rules are so simple, right? The logic feels so pure. But just beneath that satisfying surface of rows, columns, and boxes, there's this incredible physical secret, and it's hiding in plain sight. And I know what you're thinking. It sounds a little crazy. A newspaper puzzle and the physics of glassy materials? I mean, what could they possibly have in common? Well, believe it or not, there's a huge connection, and we're going to dive right into it. So, to really get to the bottom of this, we need to kind of shift our perspective. We have to stop seeing Sudoku as just a game and start looking at it the way a physicist would. And it turns out that's literally what's happening. Scientists are looking at Sudoku in a completely new way. They're not analyzing it for fun, but because the very act of solving the puzzle behaves exactly like some of the super complex physical systems they struggle to understand in the lab. So how do you even do that? How do you turn a simple puzzle into a physicist's playground? Well, it all starts by just reframing the problem. Okay, so in physics, they talk about a physical system. And all that really means is it's a collection of objects that has rules, different states it can be in, and some kind of energy. Now think about a Sudoku grid. It's got really strict rules, right? And every single number you place changes its state, and as we're about to find out, it even has its own kind of energy. All of a sudden, that simple puzzle starts to look like a perfect little miniature universe you can study. All right, and this is where it gets really cool. The concept that unlocks this whole thing, it's all about energy, the energy of Sudoku. So I want you to picture this. Imagine a huge rolling landscape with mountains and valleys. Every single possible way you could fill in that Sudoku grid, every combination, right or wrong, is a single point on this map. All the wrong answers? They're way up high on these jagged, unstable peaks. Think of them as high-energy states. But somewhere down below all that mess, there's one single deep valley, and that is the one correct solution. So solving the puzzle, it's literally like you're just trying to walk downhill to find that lowest point. And here's the absolute mind-blowing connection. You know that aha moment in Sudoku when a number just clicks perfectly into place? Well, from a physicist's point of view, that is no different than a molecule in a system settling into its most stable, lowest energy form. In Sudoku, you're finding the right spot for a number. In physics, the system is finding its lowest energy state. It's the exact same fundamental process. Okay, so systems are always trying to find their lowest energy state. But how do they actually get there? Well, a lot of the time, it happens through something you've seen a million times, a phase transition. Think like water turning to ice. Let's just take water freezing, for example. You've got liquid water, where all the molecules are just kind of jumbled up and flowing around. They're disordered. Then you start to lower the temperature. You're removing energy from the system. And what happens? Suddenly, those molecules lock into place. They form a perfectly ordered solid crystal, ice. That dramatic shift from one state to another, that's a phase transition. So that brings us right back to the puzzle. How can a simple puzzle have different phases, like water turning into ice? Well, the answer is a definite yes. And the crazy part is, if you've ever played Sudoku, you've actually felt these phases happen. And this is the absolute heart of the discovery. Okay, you know that first part of the puzzle, the easy phase, you're just flying through, filling in all the obvious, logically certain numbers. The path forward is totally clear. Physicists call that a paramagnetic transition. But then you hit the wall. You know that moment, the hard phase. You get stuck just staring at a square with like 3 different possibilities, and there's no clear next move. The system, the puzzle, it freezes. That, my friends, is what physicists call a glassy transition. It's the exact same thing that happens when materials like glass cool down too quickly. Their atoms get trapped. They get locked into this messy, disordered state, totally unable to find that perfect ordered crystal structure. So look, this is way more than just a neat party trick, right? This connection actually has some pretty powerful implications for how we understand complexity itself. This is a real model for complexity. So what's the big takeaway here? Why does this matter? Well, for one, it means Sudoku gives us a simple, almost perfect little model for studying really complex systems. It helps scientists get a handle on the behavior of things like glassy materials. But more than that, it shows how incredibly deep complexity can pop up from a few very simple rules. It really just reveals these profound physical principles that are hiding all around us in everyday life. You know, there's a line from the actual research paper that just says it all. A simple newspaper puzzle can serve as a model for studying complex physical phenomena. I mean, think about that. The humble Sudoku, it's not just a game. It's a powerful tool for decoding the very physics of complexity. And it really makes you wonder, doesn't it? If a Sudoku grid holds the secrets to the physics of glass, what other profound secrets are hiding in plain sight? What other everyday things are just waiting for us to discover the deep, complex laws of the universe that they're modeling? The answer, it seems, is probably everywhere we look.